Beste studenten, we gaan nu de les bespreken van vrijdag geleden, waar ik in Duitsland was, in Oberwolfach. En ik bespreek nu het volgende hoofdstuk. Dat gaat over de zogenoemde Goodstein rijen. I should do it in English. So the next section is about Goodstein sequences. Now, what are the Goodstein sequences? Well, the Goodstein sequences come with a combinatorial assertion, speaking about finite numbers, and they will describe process, and the process is so complicated that termination of the process cannot be shown in Peano arithmetic. I would expect a very complicated process, but in fact, it's some of the most simple possibilities to write down an assertion which is true but not provably so from the Peano axioms. So to give it a start, fix a number k at least as big as 2. Now k is chosen to develop numbers with respect to base k. So lemma 4.1. Well, we define what is the normal form of a number. Now, if a number m is 0, then 0 is its normal form. But if m is bigger than 0, then we find unique numbers p, q, and r such that m can be written with respect to an exponential representation with respect to base k. We write m as k to the r times p plus q. And now there are the expected side conditions where k to the r is less than or equal to m less than or equal to k strictly less than k to the r plus 1. So we sandwich m between k to the r and k to the r plus 1. So this covers even the case m equal to 1, then r will be equal to 0. But moreover, this number p has to be smaller than k. So this number p here. And now we want to have that the rest here, this q, is smaller than k to the r. In this situation, this is a unique representation. We write m is in k normal form equal to k to the r times p plus q. And if m was 0, then m is also in k normal form equal to 0. So every natural number gets a unique representation. Now, having fixed, well, how to prove this? Well, it's division with remainder. So I don't prove this. Proof of the lemma. This is discrete mathematics 1. So first you sandwich m with respect to k to the r. And then you look how often you can fit in k to the r into m. And once you have done this in an optimal way, then you look for the remainder, which has to be less than k to the r. Because if q would be bigger than k to the r, then you could change either p or k to the r. Okay, that's fine. And this is used now to define the base change operation. Definition 4.2. So assume what? We assume m is not 0. M has k normal form k to the r times p plus q. Now we replace in m every occurrence of base k by a new base k plus 1. So then m, and now it's a short definition, m in brackets k is given by k plus 1. So we replace this base here by k plus 1, but we do it in a hereditary way. So we do the change in the exponent. Now p is smaller than k, so there's nothing to be changed. And we do all the base change in q. And of course, if we have number 0, there's nothing to be changed. It remains 0. Okay, this is a base change operation. And now you can easily imagine that this preserves monotonicity properties. So we have the following lemma. So if m is smaller than n, then after base changes, m where the base is changed is smaller than n where the base is changed. This is basically clear because the comparison between m and n is done by the comparison between the normal forms, and in the normal forms we apply a monotone operation. Now another trivial operation, trivial insight is m is less than equal to m after base change. Yeah, well, we just made at every occurrence of k bigger than k, then we moved it into k plus 1. And if you do it everywhere, then of course it's clear that the result will become bigger. Of course, if m is 0, nothing will change. Could have equality. Now, the important insight now is if m is in k normal form, equal to k to the r times p plus q, then what happens after base change? Well, we get the k plus 1 normal form. K plus 1 to the r of k times p plus q with base changed. These are more or less obvious properties, but let us prove one of those, or maybe two of those. Well, the property C is most important, but let us first check A. So we assume that m and n are non-zero, otherwise the assertion is not interesting. We assume m is in k normal form, k to the r times p plus q. N is k to the s times t plus u, k normal form. And okay, what can happen? Well, we have here this property that in base representation, this m is bounded by k to the r plus 1. What does this mean? If r is smaller than s, there's already a big difference between m and n. So, well, if r is smaller than s, then we obtain the following. Well, we do induction on natural numbers, so we can assume monotonicity for smaller values. Now, m, where we do the base change in k, is k plus 1. Here we have r of k times p plus q of k. Now, r of k will be smaller than s of k by induction hypothesis. So this is less than equal to Here's k plus 1. And now here I replace r of k by s of k minus 1. Aha. Now q is smaller than k to the r. What does this mean? Q is smaller than k to the r, then q of k is bounded by k plus 1 to the r of k, and r of k is bounded by s to the k minus 1. So this is less than equal to k plus 1 to the s of k minus 1 times p plus k plus 1 to the s of k minus 1. Now here's times p. P is smaller than k, so in total this is bounded strictly by k plus 1 to the s of k. And now this is clearly less than equal to the base change over here. Now I have to make one assumption. I didn't write it here. This p is assumed to be bigger than 0, because otherwise there would be some ambiguity. So p plus 1 is bounded by, p is bounded by k. P plus 1 is bounded by k plus 1, so we get this bound here. And so we obtain this is bounded by n of k. Aha, that was easy. That was the first case where r is equal to s. And now we continue lexicographically. So this term is now equal to this term. Next situation is p is smaller than t. And this works the same way. If r is equal to s and p is smaller than t, then we obtain what? M of k is k plus 1 to the r of k times p plus q of k. Now q of k, q is smaller than k to the r. So this is bounded by k plus 1 to the r of k times p plus k plus 1 to the r of k by induction hypothesis. This is less than equal to k plus 1 to the r of k times p plus 1. But p is smaller than t. So the bound is bounded by k plus 1 to the r of k times t plus some extra, which does not matter. And this gives n of k. Aha, it was easy going. Now there's some last one. Namely, last case is, so we have the kind of normal forms, so exponential based normal forms for m and n. Last case is if r is equal to s and p is equal to t and q is smaller than s. Induction hypothesis gives that q of k is smaller than s of k. So induction hypothesis is what? M of k comes term for base change here, r of q times p plus q of k. And now if we copy the first part, r of k is the same as s of k. P is equal to t, so this term the same as this term. Q of k is now by induction hypothesis smaller than s of k. S of k. This is n of k. Aha. B. B, what was B? B was this trivial estimate, which is proved easily by induction on M. I will leave this to you. It's a trivial verification. Now, I just write that this is simple. C. C is also simple, but it requires an argument. So assume what M is in K normal form, K to the R times P plus Q. We have K to the R is less than equal to M, smaller than K to the R plus 1. P is smaller than K. Q is smaller than K to the R. Then M of K is what? K plus 1 to the R of K times P plus Q of K. What has to be checked? Has to be checked is this one is smaller than K plus 1 to the R of K. This one has to be smaller than this. M of K has to be bounded from below by this one, that's fine. And from above by K plus 1 to the R of K plus 1. It's also not too difficult. And P has to be smaller than K plus 1, but this is clear because P is already smaller than K. So let us take this. We have Q of K is smaller than K plus 1 to the R of K. This follows from assertion A. Moreover, we have P is smaller than K, hence smaller than K plus 1. And now in total, we get what? Well, of course, K plus 1 to the R of K is less than equal to M of K, which is K plus 1 to the R of K times P plus, and this is now here the bound, plug in for Q of K. So we take here K plus 1 to the R of K. Now you see here in total P occurrences plus another one. So this is bounded by K plus 1 to the R of K times P plus 1. P is smaller than K, and P plus 1 is strictly smaller than K plus 1. So this is strictly bounded by K plus 1 to the R of K plus 1. Aha, so, and this is finally needed to show that this term here is in Goodstein in K normal form. Okay, now we come to the Goodstein process. 4.4. Definition of the Goodstein sequence. Well, Goodstein sequence starts with a given number, so let M be your favorite number, let M be given. Now we start our process time 0 with M. Now if the sequence, well, of course, let us assume that M is bigger than 0, otherwise it's not interesting. If M L is different from 0, then we make M bigger in the next step. So in the transition in time from L to M L plus 1, we do what? We take previous number ML. Now base change only makes sense for numbers for bases which are bigger than 1. So we do base change. We develop ML with respect to base L plus 2. And then we replace hereditarily base L plus 2 by L plus 3. So this makes the number bigger, and then I subtract 1. And otherwise, if ML is 0, we put ML plus 1 equal to 0. Now, what is this theorem? Theorem is the following. First of all, you can implement the Goodstein process into your computer. And when you start, let's say, with m equal to 10, you will see that this is a diverging sequence. At least the computer will tell you that this is diverging, but the corresponding theorem is the following. Namely, that n makes true for all m. There exists an L, ML hits 0. So I start with a big number m, let's say 1 million. And I start up my Goodstein process, making numbers bigger and bigger and bigger. So on the computer, I will produce a Stack Overflow. But then at some moment in the future, things will turn otherwise. You get a big number, and then you will always subtract 1, and finally you will hit 0. And the second one, BA, does not prove for all m is L such that ML hits 0. Now we will not do proof theory here, but we will show that the dependency of L of m is of magnitude h epsilon 0 of m. Okay, now we prove A. The problem in the proof of A is, if you haven't seen the proof, you have no chance to do it by just discrete mathematics. Now, since we already know how to deal with our ordinals, so we have 4.6 definition. For this, we use our function class E, coding well ordering. We define dk of 0. Well, 0 is mapped to 0. And if m has the form k to the r times p plus q, then ck of m is equal to omega to the ck of r times p plus ck of q. So what's going to happen here? We do a base change. We hereditarily move k into omega, and we do this also in the exponents and in the remainder term. Now this is a natural operation, and it has all the natural properties. So what are the natural properties? It will be 4.7 lemma. Now, first of all, ck is a monotone operation. It's not that a big surprise. B, now it's a bit funny, but it's absolutely crucial. Namely, if m is a form cantonal, it's a base k normal form, q to the r times p plus q, then ckm is an ordinal. And this will have the following property. It will have a normal form property. namely it's omega to the pk of r times p plus pk of q. What does the normal form property mean? It means basically that this term here is not eating up any term of those summands, and actually this term here will be smaller than this one. So normal forms on natural numbers are moved to canonical normal forms of ordinals. And this is a deep insight because later I extended Goodstein and this was always working. That nice normal forms on numbers go over to nice normal forms of ordinals. And C is easy to understand. So take number m and replace hereditarily base k by omega. And the same as we first take m, we replace every occurrence of base k by k plus 1, and then we move afterwards k plus 1 into the omega. Now how can we prove this? Well, the proof of A is basically the same as before, where we showed monotonicity after base change. But well, this is a lecture, so I will give some sort of argument. Case 1 was what? Well, let's first fix. M is k to the r times p plus q. N is k to the s times t plus u, let's say. So this here is an n. Now, assume that m is smaller than n. Case 1 is r is smaller than s. But then it's simple. Apply induction hypothesis. And we obtain pk of m is omega to the pk of r times p plus pk of q. This is less than equal to omega to the what? Well, here we apply induction hypothesis to this term. So we obtain this is bound by omega to the pk of r times p plus the other term. So here's p plus 1. And now we use the property that values of the form omega to the pk of s are closed under addition. These are additive principal terms. So pk of r is smaller than pk of s. Then the finite number of segments here is smaller than this thing here. And this is less than equal to omega pk of s times t plus pk of u, which is pk of n. Now, second case is r is equal to s and p is smaller than t. Now, what's going to happen? Then we obtain pk of m omega to the pk of r times p plus pk of q smaller than omega to the pk of r times p plus, well, now the induction hypothesis says what? This term here is bounded by this term here. So it's bounded by this term plus 1. And now this is bounded by, yeah, p plus 1. You see here is bounded less than equal to t. So this is less than or equal to ck of n. Third one, r is equal to s, p is equal to t, u is smaller than u. Then ck of m to omega to the ck of r times p plus ck of q smaller than omega ck of s times t plus ck of u. So why is this the case? This term here is the same as this term. P is equal to t. And this one is smaller than this term by induction hypothesis. And then we use laws for comparing ordinals. And this is then ck of n. This is u. Okay. Now, next part is we have to show that normal forms are preserved. But that's not too difficult. Let us now prove B. M is assumed to be in K normal form, K to the R times P plus Q. And of course, Q is smaller than K to the R. And this means CK of Q by A is smaller than omega to the CK of R. And this means what? This means omega to the ck of r times p plus ck of q is in normal form. So this was easy, and C is also easy, but let us prove this. So it looks trivial, but there is a problem. What is the problem? Well, not a difficult problem, but you have just to be careful that you have to observe a problem, possible problem. So let assume that, as usual, m is not 0. So we write m as K normal form. And then what? Then ek plus 1, mk plus 1 is what? It is ck plus 1. And here we have k plus 1 to the r, where do base change in k, times p plus q, where do base change. Now comes the point. This is K normal form. We need that m after K is in K normal, K plus 1 normal form. As a form K plus 1 to the R of K times P plus Q of K. Now this is used here, the next step. This is the most important. We have to recognize that this expression is a K plus 1 normal form, because the function pk works only on normal forms, and then it moves k into omega. That's a part of the proof which is non-trivial, just to have the right preparation. Now if we do so, then we have here omega to the ck plus 1 of r of k times p plus ck plus 1 of q of k. Aha. Now what? If we can apply induction hypothesis, we obtain omega to the pk of r times p plus psi k of q. This is an R. Well, and this is ck of m. Aha. So after all, it was simple, but we needed the corresponding preparations, namely that k plus 1 representation it comes from a k representation. Okay, now we did lots of stuff, proving monotonicity of base change, proving monotonicity with this ordinal interpretation. Now we have a bit of space left. The remaining space I prove we prove termination of the Goodstein sequences. So we have M0, M1, ML, and some moment we hit 0. Well, what we do is we associate here ordinals which form a strictly descending chain. That for sure will stop at some moment. So what we do is we assign an ordinal to the nth step, k steps, let's say, or maybe nth step, it doesn't matter, in the game. So what do is we take number ml, the Goodstein sequence entry at time L, and we apply function psi L plus 2 to it. So this is basically the number associated here, namely we use this ordinal function. Now it's important, what is important? Well, the number starts here with L equal to 0, but base changes can only be made for bases, or in reason being, only for bases at least as big as 2. Therefore, I'm adding here this plus 2. Okay, now what? If at time L, the Goodstein sequence is not yet 0, what's going to happen? Then OM L plus 1. Now what is this? That is equal to psi L plus 3 of ML plus 1. Cool. Now we plug in the definition of the Goodstein number. So what is this? This is psi L plus 3. We have M. We replace what? We replace base L by L plus 1 in ML. Let me look back in the definition of the Goodstein sequences. Aha, here I was wrong. So if I define ML plus 1, I have to use here L plus 2. So that I have to do. So take here ML and we replace base L plus 2 by L plus 3. And then we apply the psi function. But in the Goodstein process, we also have subtracted 1 over here, which is most important. Now this is smaller because pk or pl plus 3 is a function. This one is strictly monotone on these arguments. So if I make the argument bigger, I get pl plus 3, and here I have ml plus 2. And this is the same as what? So what do we do here? We take ml, we replace in the base L plus 2 representation, L plus 2 by L plus 3, and then we move L plus 3 into omega. Instead, we could just directly move L plus 2 into omega for number ml. That's one of the lemmas which we did before. And this is OML. So what's going to happen is if ML is not yet 0, then I get a decrease in my Arnold function. Now this cannot continue forever. At some moment, we have to stop. Okay, so conclusion is if for all L, ML would be different from 0, then we would have for all L, O of M, L plus 1 smaller than O of ML, contradiction. Therefore, this is wrong. There exists an L such that ML hits 0. That's good. Now we want to prove what? This one here. BA does not prove totality of the Goodstein principle. Now what we have seen until now is that we have used our ordinals in E to show independence. We have used our ordinals in E to show domination. The question is whether we need the full power of E or not. And in fact, we need somehow the full power of E. And it will come now. For this, I study a small lemma. Easy to prove. So what do we prove? I take my number m, consider mk, and then I subtract the 1. So this number is smaller than mk. And then, so here I replaced k by k plus 1. And then first it's a base change, and then I subtract the 1. And if I take now the Arnold mapping pk plus 1, so this number here is smaller than pk plus 1 applied to m of k. And that number is pk of m. So we know this number here is bigger than pk of m. But it's also somehow restricted in decrease. If you take that number, pk of m is bigger than this number. So let's consider this number. So again, pk of m, this number here is bigger than this number because this number applied to m of k is just this number. So pk of m is bigger than this number. Now but this number here, what can we say? So how much bigger is this number, or how much smaller is this number than pk of m? And we can measure this in, if we go in the fundamental sequence for pk of m at argument k minus 1, then the sign will change the same. So we have now sandwiching between this number and this number. And this is what is used in the unprobability part. Namely, we do sandwiching of these numbers in between two consecutive elements in a fundamental sequence for for the numbers pk of m which are involved. Okay, too much said already, so we go into the proof. Induction on m as usual, and assume m has the form k to the r times p plus q. There are three cases. First case is q is bigger than 0. What can we say? Well, we do induction on the number m. So psi k plus 1 of m of k minus 1 is psi k plus 1 of k to the r times p. Where do the base change? Plus the function pk is monotone. Yeah, so it can therefore be moved into the sums. So pk distributes over sums. So if I subtract from the whole number a minus 1, it's the same as subtracting a minus 1, a 1 from q and putting the result additively to k to the r times p. Now here we apply induction hypothesis to obtain pk. But in the first part here, we also move the base. So we have this law for calculating compound replacements. So here we have first base change in k, from k to k plus 1, and then we move k plus 1 into omega. We already know that we can directly move this number into omega. In this number, we can move k to omega. And here we have psi k of q at argument k minus 1 by induction hypothesis. Now, since this here is an ordinary Cantor form, the definition of fundamental sequences says this is the same as pk of m, where I applied number k minus 1. And we assume in the lemma that k is at least as big as 2. Maybe at least as big as 1 is sufficient, but anyway, it doesn't matter. Now, the next case is q is equal to 0, and p is bigger than 1. Now, what is psi k plus 1? M of k minus 1. It's the same as, well, we have here q equal to 0, so m is k to the r times p, which is k to the r times p minus 1 plus k to the r. Okay, so we subtract the minus 1 over here. So what do we obtain? This is psi k plus 1 of k to the r times p minus 1, base change in k, plus psi k plus 1 k to the r minus 1 stop. So we consider the base change in k. And then we have to do what? We have here k to the r minus 1. Where I do base change in k. Now here we obtain in the first part can apply the laws for composition. So it's pk k to the r times p minus 1. That's fine. Plus, and the second one we can apply induction hypothesis to obtain bigger than or equal to ck k to the r of k minus 1, which is ckm at k minus 1. So if you look at this one, pk of m is omega to the pk of r times p. But now we use here just the part on the last cement. Okay, and then the whole thing here is alpha plus beta at the fundamental sequence. This is the same as taking alpha plus beta as a fundamental sequence. This is what is needed here. Okay, now we have seen 2. Now we have seen number 3. Q is 0 and P is equal to 1. Then pk plus 1 of mk minus 1 is equal to what? Well, now it's interesting. So we carry out the definition. Now we have to use the binomial sum. So we could evaluate it in full terms, but we just make an estimate and take the first sum. It's the exponential sum. So we have here k plus 1 to the r of k minus 1 times k. This is by induction hypothesis. At least as big as omega to the psi k plus 1. As the induction hypothesis is just a definition at this moment. Psi k plus 1 of r of k minus 1 times k. And now comes induction hypothesis, at least as big as omega to the psi k of r at argument k minus 1 times k. And this is at least as big as omega to the psi k of r fundamental sequence at k minus 1. There are two cases. One case is that we have pk of r is a limit, then the fundamental sequence is given by this term, by this term. Or this is a successor ordinal, and you have to if pk of r is a successor, then pk of our predecessor is just thing minus 1. And then we have to multiply at the bottom with a factor k. So the proof is done. This lemma is a key to prove unprovability of Goodstein in pair-arithmetic. And we reduce the question to the unprovability of the Hydra battle in pair-arithmetic. So proof of 4.5b. Okay, assume PA proves for M that exists in L such that ML hits 0. Yeah, if it proves for every M, and then also for all instances which I can put in for M, then PA does prove for all K. There exists L such that 2 index K, L hits 0. For every K, we build an exponential tower of height K, and then we consider Goodstein it, this number. Okay. Now, what we are proving is these numbers L, depending on K, grow like the Hardy function of ordinal omega index K. And this is an proving independence. Well, we don't go into the proof theory of PA, but we just compare statements with respect to growth rate of the underlying sequences, of the growth rate of the underlying functions. When the function has h epsilon 0 as a lower bound, and then the corresponding statement is already unprovable. And when the function under consideration, the recursive function under consideration, is bounded by an h alpha for alpha smaller than epsilon 0, then Piano does prove the statement. Anyway, we have what is C2 of 2 index K? Okay, we go into this term and replace 2's by omega. So this is omega tower of height K. So it's omega tower of height K. Okay. Now, let M0 be equal to 2 index K, and M L plus 1 equal to, take ML, and I replace L plus 2 by L plus 3 and subtract 1 if ML is different from 0 and 0 otherwise. Would alpha 0 be equal to omega K, and alpha L plus 1 be equal to, take alpha L, and now it doesn't really matter. I think I take here L plus 1 for L, but this is not so important. What is important that we form the ordinals associated to a hydra battle. So at every step L, we get in the fundamental sequence one step higher, proportional to L. We do have, well, consider again consider what? OML being equal to C L plus 2 of ML. And what we have? OM0, M is 2K, this is C2 of M0, this is omega K, this is alpha 0. So now what is the plan? We have here the sequence alpha 0 going to alpha 1, going to alpha 2, stepping down. And then here we have O of M0, O of M1, O of M2. And we know already this is a descending sequence. Now we know this sequence here becomes long. Now this sequence could become short. But what we will see is we interweave this sequence into this sequence. So to say, we squeeze in these numbers somewhere. Every situation here, we squeeze in some of these numbers. This means the number of steps here is as big as the number of steps stepping down over here. And the lower bound here was unprovably large. Okay, now what is the claim? The claim is following. O of ML is at least as big as alpha L. So what does this mean? The first time where alpha L hits 0 is at least as big as the first time where OML hits 0. Now we want to prove this. For this, we consider the less than or equal to relation with respect to an index L. What does this mean? This means, as I already said, that if you take this number and step down the fundamental sequence only along L, then finally we hit this number. So this index L is needed to for the induction. And afterwards, we forget about this L and know that this number is at least as big as this number. But to prove this assertion without the L, we have to use the assertion with L. So assume now that what? OML is at least as big as alpha L. And this number here is CL plus 2 of ML. Then what? What can we say about OML plus 1? We have to compare this number here, this index L plus 1, with the number alpha L plus 1. Well, let's just have a look. How does it calculate? So this is psi L plus 3 of ML plus 1. Now, assume that ML is different from 0. Can we assume this? Well, the answer is yes. So we prove this one for all L such that these numbers, let's say, are bigger than 0. And all these numbers have to be bigger than 0. Okay. Now this is this number. So what is this? We plug in the definition. CL plus 3 of ML, L plus 2 minus 1. Aha. Now we are in the situation where we can apply our crucial lemma. This is the term. So what lemma do we apply? We apply this one here. There are 3 players. We have what? We have this k plus 1, then a number. We do Bayesian from k to k plus 1. And we have the number k minus 1. And here's pk plus 1, and here is pk. Now if you apply this, we got what? This is at least as big as. So the index here goes 1 lower. Here we go to ML and take the result and have to evaluate it with L plus 1. That's by the lemma. Okay. Now by the Bachmann property, you can also see what? No, Bachmann property is not needed. We have this situation. So what? This is the same as O of ML at argument L plus 1. So that's good to know because of what? Because of what we have the O of ML bigger than O of ML plus 1 bigger than O of ML is L plus 1. Aha. Now we see here's O of ML, here's O of ML. Here's it O of ML at the fundamental sequence. So this means by the Bachmann property, we can step down from this number along fundamental sequence with arguments 0 to this number. So what does this mean? This means O of L plus 1 steps down along 0, hence it steps on along 0, it steps down along L plus 1. We finally hit O of L of L plus 1. Now O of ML goes down to alpha L. What does this yield? This yields that O of ML. Now apply fundamental sequence at argument. I have to check. So alpha L plus 1 is alpha L at argument L plus 1. If I have here argument L plus 1, I can step down at here alpha L plus 1, which is alpha L plus 1. So if it is possible to step down here along L, if a lemma that we can here replace L by L plus 1, that's fine. So if we step along this number at L plus 1, finally we will hit this number. So what does this mean? If we step down along L plus 1 here, finally from these numbers we will hit this number. The only exception is if this number is equal to this number, and this number is equal to this number, L plus 1 is here and here. So in both cases, I can step down from this number along L plus 1 to hit this number, which is this number. And then I can step down from this number along L plus 1 to this number, which is this number. I can step down along L plus 1 to hit this number. So in total, we have seen that OM L plus 1 steps down at L plus 1 to alpha L plus 1. Aha. So, hence, the least L such that ML hits 0 is at least as big as the least L such that alpha L hits 0. But alpha 0 was omega k. And so basically the higher numbers are lower bounds for the Goodstein numbers. Here is the length of the higher battle for omega k and slightly enlarged indices, which makes the higher battle even longer. So this shows that Bernoulli is not provable, is not able to show the probability of M L hits 0 for a big number L. Okay, that's the first part. And now we have to deal with phase transitions. But first I will take a small break and I will continue in a short amount of time. Okay. We have seen now the basic results about Goodstein sequences. And there's something which can be discussed here, namely, in what way can we generalize this? And in the last years, I worked on this. And we can replace the normal forms with respect to the exponential function by other normal forms, let's say based on the Ackermann function. And this leads to stronger Goodstein sequences. It's an interesting enterprise, but I will not cover this in this lecture, but I have several publications over this. So interested people can have a look. But this also requires higher ordinals, which we haven't covered yet. So if you want to go to what's called gamma 0 or the Howard-Bachmann ordinal, then one has to use new systems of normal forms. What we now do is we consider the phase transition. What is this? It's getting a bit blurry. I see. Now it should be better, maybe, hopefully. Okay. So what we do is we start with a phase transition function. Assume with a function f from natural numbers. Now we do phase transition with respect to f. And in this context, it seems to be useful to assume a bit, namely that f is sub-exponential. We also assume that x is less than or equal to f of x. And if x is less than or equal to y, then we should have that f of x is less than or equal to f of y. Now, this property here is something which we did not have in the situation with the Hydra battles. Remember, there we had the function log 2, and then we iterated, let's say, alpha many times, at alpha inverse many times, applied to argument I. And this function, every now and then, goes downwards, not upwards. Very seldomly, but this is not monotone. Not weakly monotone. Now, why do we assume that the function f is monotone? Because base change needs monotonicity for structure preservation. So assume the process of m, and I take base k, and I replace by k minus 1. What can happen? What is the problem? The problem is, assume that we have a number k to the r times k minus 1. If we here replace k by k minus 1, what's going to happen is, when we get here k minus 1, and we have r, k goes to k minus 1. But k minus 1 stays. And this suddenly becomes k minus 1. R of k goes to k minus 1 plus 1. And so it's very difficult to, well, this term here is now a different structure. So we say here suddenly a plus 1, which by hereditary means can have a huge effect. And so if m is a normal form with respect to base k, then if you replace base k by k minus 1, the result is no longer in k minus 1 normal form. And this leads to problems. And I had this publication with Frederick Meskens, and somehow the publication doesn't work for non-monotone functions. So there's a problem. This publication actually only works for monotone functions. At least currently, I don't know how to fix this. So this is a research project to consider the article by Meskens and Weiermann, and just to check whether it also holds for those functions, including the non-monotonicity situations. Now, in the meantime, I have no idea. So I still believe that the results are true. The only problem is how to deal with the non-monotonicity and to measure how often I have non-monotone situation and how does this affect the process. I don't know yet. So to make things easier, I now consider only monotone functions. Now define relativized Goodstein sequences. So M0 is M, and ML plus 1, index F, is I take ML, I go into the base, and develop ML with respect to base FL plus 2 and replace base L plus 2 by FL plus 1 plus 2. Now, I assume that you know, can believe, you can guess what this means to, what this notation refers to. So I go into the FL plus 2 normal form and replace everywhere this number by this number, where the base occurs in the exponents and also in the remainder. And then we have the following theorem. Namely, for every m, there exists an L such that MFL hits 0. That's fine. B, let f of x be the following function. Now I make the function log 2 of h epsilon 0 inverse of I. I make it a monotone function. And then EA does not prove for all m there is L such that MFL is 0. And C, let f alpha of x be maximum I less than equal to x log 2 h alpha inverse of I for alpha smaller than epsilon 0, so for alpha in E. Then PA does prove for all m there exists an L such that MLF hits 0. Okay. So how to prove this? Now this is very easy. For this, we use the corresponding result for the Hydra battle. And for this, we also use the corresponding result for the Hydra battle. But details are not so straightforward. So somehow we know from the last discussion on Goodstein sequences that the ordinals associated to the members of the Goodstein sequence can be interleaved with the ordinals showing up in the termination stepping down process for the Hydra battles. Now, plan is to do the same here. So proof of A, it's easy going. Let O of ML be, now L is replaced by F of L plus 2 of MLF. And then we can make the classical argument. If we are not hitting 0, then O of ML plus 1 is what? It's psi FL plus 1 plus 2 of ML plus 1 of F. So this is what? It's psi FL plus 1 plus 2 of MFL, where I have F of L plus 2, replaced by F of L plus 1 plus 2 minus 1. Now what? The psi functions, this one here, is monotone in this argument. So if I drop this minus 1, I get this is smaller than psi FL plus 1 plus 2 MFL, where I replace FL plus 2 by F, stop. FL plus 2 is replaced by FL plus 1 plus 2, and then no minus 1. This is the same as psi FL plus 2 of MFL. Now this is clear if what? If FL is just if F is 1, if 1 plus F of L is the same as F of L plus 1. So if the distance between those numbers is precisely 1, I can use lemma from before. But it could be that FL is equal to FL plus 1. Now what's going to happen then? Now this FL plus 1 is the same as this one here. And if FL is equal to FL plus 1, then there's no change involved. So I get here FML. So this also works in case that this works for FL plus 1 is F of L plus 1, and also for FL plus 1 equal to FL. And this one here is O of ML. So here we have strict less than. So this number here at time L plus 1 is smaller than the number at time L. That's fine. Perfect. Okay. Now we prove the unprovability part. Now what is the plan? The plan is as before. Plan is interweave O of ML with stepping down along the fundamental sequences. So we have O of M0, and then we start at F of 0, then F of 1, F of L, etc. And if we can do this, then we are fine. But the problem is how to do so. First trick is we define a predecessor operation on ordinals, Px alpha. Predecessor of 0 is 0. Predecessor of alpha plus 1 is clearly alpha. And if lambda is a limit, the predecessor of lambda is the predecessor of lambda x. So what does this mean? Well, this means we take a lambda, step down to lambda x, step down to lambda x of x, until we hit here some number beta plus 1, and then we give output beta. So we step down in the fundamental sequence until we hit the successor, and then we go to the predecessor. Okay. Now in a minute I will explain where it is necessary for. The next lemma is the following. If alpha and beta are a normal form for addition, then the predecessor of alpha plus beta is alpha plus the predecessor of beta. And B, this happens for beta different from 0. What is the predecessor of omega to the alpha? X predecessor of omega to the alpha is the x predecessor of what? Take your omega to the predecessor of alpha times x plus 1. And from this number, the predecessor. This works for alpha different from 0. Now, this looks a bit strange, but both of them are easy to prove. Proof of A, well, what could happen? Beta could have a form of a gamma plus 1. Then what? And then Px alpha plus gamma plus 1. Well, this is successor, so it's alpha plus gamma. And this is the same as alpha plus the predecessor of gamma plus 1. So this is trivial. And second, if beta is a limit, then we have that normal form applies to alpha and beta of x. And we have what? Px alpha plus beta is, well, you have to calculate what is the fundamental sequence for this number. This is alpha plus beta of x. So we get Px of alpha plus fundamental sequence of beta at argument x. Now we can apply induction hypothesis. This is alpha plus Px of beta of x. So by magic. And this is alpha plus the predecessor of beta. That's a cool argument and really magic. And the same magic applies to the other situation in B. So we prove B using A. So if alpha is a limit, then alpha x is different from 0. Because, yeah, alpha x is at least as big as 1. That's good. So we can apply induction hypothesis. So Px of omega to the alpha is what? Px of omega to the alpha at argument x. By induction hypothesis, this is the same as Px of omega to the Px of alpha of x times x plus 1, which is Px to the omega to the Px of alpha times x plus 1. And the other cases, alpha is a successor gamma plus 1. Then you have Px of omega to the gamma plus 1 is what? Is Px of this number at fundamental sequence is omega to the gamma times x plus 1. Now by A, this is the same as omega to the gamma times x plus Px of omega to the gamma. Now this again what is this? Oh, I think I make a bit of overkill here. Let's just look here. So this is Px of omega to the Px of gamma plus 1 times x plus 1. So that is a shortcut. So we are done. We are immediately done. It's just let's see, maybe no, this seems to be correct. Yeah, correct. A very short proof. Okay, even better. Aha. Now, what can we do with these Px functions? Well, the explanation comes now. Next lemma is the question, how do they interweave with fundamental sequences? Px of alpha is at least as big as alpha fundamental sequence is x minus 1 for x at least as big as 2. Now, x at least as big as 2 is fine because we start with basis representations which are at least as big as 2. So now we prove this lemma, and this is very simple. So alpha is, let's say, gamma plus 1, Px gamma plus 1 is gamma, which is the same as gamma plus 1 at argument x minus 1. Not much to show. Alpha a limit. Px alpha is Px alpha x by induction hypothesis is bigger than alpha x at argument x minus 1. Now I claim that this is bigger than alpha x minus 1. And the reason is because we step down from alpha x, and then this steps down at 0 to alpha x minus 1 plus 1. Maybe I need here index 1, but it doesn't matter that much. So whatever I do from this number here, I can do stepping down along x minus 1. And I will not go directly below this number. So some stepping down, I will hit this number. Okay. And what do I else need? I need what? Another lemma, namely ck plus 1 of mk minus 1. We know this term, I've seen it before. Is at least as big as ck m minus 1. Now, how to prove this one? Well, it's simple. ckm minus 1 is less than ck plus 1. We take this number m minus 1 and do the base change in k. So actually there's equality. Now m minus 1 k is strictly smaller than m of k. So this is less than equal to ck plus 1 m of k minus 1. Because we have this strict inequality here. Strict inequality yields that this is less than equal to this number. And there we are. Okay. Now we do an abstract lemma. For a weakly monotone function f. Let beta 0 be O of m0 and beta l plus 1 be equal to beta l f of l. Claim O of ml is at least as big as beta l. Now, what's the point? The point is we will apply it to the function which we know from the Hydra battle, using phase transition for those numbers. That was the function f being equal to log binary log iterated h epsilon 0 inverse many times. That's fine. And the function which we are considering in the proof of B is even growing slightly faster. So if the Hydra battle is unprovable, and the corresponding Goodstein sequence is unprovable. Now to prove this, well, actually we know how to prove this. We have seen something similar before. So this is by induction on L. So that's easy. OM0 clearly is equal to beta 0. Therefore, this is true for L equal to 0. Now, to prove it, actually, we plug in here the stepping down relation along FL to make inequalities work. So assume we have what? O of ML, least as big as FL beta L. Then we have what? Now we have to be very careful. O of ML plus 1 is what? Psi f of L plus 1 plus 2 ML plus 1 of f. Right. Now assume that MLF is not yet 0. It's psi L plus 1, psi f of L plus 1 plus 2. MFL, we replace base FL plus 2 by base FL plus 1 plus 2 minus 1. Now I use my lemma from before, namely this one here. So we replace this one by minus 1, and then we get rid of the base change. Okay, we do so. So if f of L, if 1 plus f of L is equal to f of L plus 1, we can use the lemma and obtain that at least as big as psi f of L plus 2 mfl minus 1. Now, what happens if this number is equal to this number? Well, then I don't do any base change at all. This number will be this number. And if FL is the same as FL plus 1, so in both cases, we have this inequality. That's fine. Aha. Seems that I missed a lemma. An important lemma indeed. Great. Anyway, it doesn't matter. Namely, the claim is now this is the same as the predecessor of FL plus 2 of psi FL plus 2 of MFL. So this comes later. If this is going to be true, then this is at least as big as the lemma which we have seen. Psi of FL plus 2 of MFL of f of L plus 1. And this is O of ML. So this is at least as big as O of ML at argument f of L. So what we have? O of ML by induction hypothesis at least as big as beta L. And what does this mean? This means that O of ML, where I plug in here f of L, at least as big as, with respect to f of L, to beta L of f of L, which is beta L plus 1. Aha. So from this number, can step to beta L plus 1. Now we have to show from this number, stepping down at f of L, we hit this number. be careful, he is only at least as big as, so it's not pointwise equality. Anyway, it doesn't matter that much. We have what? O of ml bigger than O of ml plus 1, at least as big as O of ml f of l. Now, Bachmann property implies what? That this here can be stretched into an f of l. So O of ml plus 1 steps down to f of l, O of ml, f of l steps down to beta l plus 1. And once we have this, then, of course, we can make f of l bigger. O of ml plus 1 also steps down along f of l plus 1 to beta l plus 1, and we can continue. Okay, now from the unprovability of the Hydra battle, for f of I equal to log 2 h epsilon 0 inverse of I of I, we can conclude the unprovability PA of the statement for all m there exists L m L g hits 0 for function growing slightly faster than f. G of x is the maximum taken over I less than equal to x, log 2 of h epsilon 0 inverse of I, and then rounded to natural numbers. Now the point is why I need this maximum here, just to be sure that I only apply base changes upwards and never downwards. Now this is all fine, but there was some gap in the proof, which I just recognized. That's very interesting. So what was the gap? This one, yeah. That's very interesting. So we have to prove a lemma. What could be the lemma? The lemma is what? Px of m minus 1 is the same as no, stop. What was it? Yeah. Ck of m minus 1 is the same as pk psi of m. So let us calculate this one. This is some interesting thing, and this finishes the unprovability part. So proof. Well, we write m as we assume. What happens if m is 0? That's also fine, right? And if here left 0 and right 0. Now assume that m is k to the r times p plus q. Assume q is bigger than 0. what is pk of m minus 1 is the same as pk of k to the r times p plus q minus 1. So what? This is omega to the pk of r times p plus pk of q minus 1. What is now pk of ck of m? It's pk of omega to the ck of r times p plus ck of q. This is by laws for the pk function. Pk distributes can be calculated by the pk of the last term because this term is smaller than this term. So this is omega to the pk of r times p plus pk of ck of q. And these two terms are the same by induction hypothesis. Great. Next one. So now m is k to the r times p. Q is now 0. And assume that p is bigger than 1. What is pk of m minus 1? It is pk of k to the r times p minus 1 plus k to the r minus 1, which is the same as omega to the pk of r times p minus 1 plus ck of k to the r minus 1. Ck of m, and then pk of this is pk of omega to ck of r times p is the same as omega to the pk of r times p minus 1 plus pk of the last term, which is omega to ck of r. And this is the same as omega to the pk of r times p minus 1 plus pk of ck of k to the r. And these terms are equal by induction hypothesis. Great. Now finally, assume m is k to the r. What is going to happen? And then what? Ck of m minus 1 is ck of k to the r times k minus 1 plus, oh yeah, yes, minus 1, plus k to the r minus 1 minus 1. So this gives omega to the ck of r minus 1 times k minus 1 plus ck of k to the r minus 1 minus 1. Cool. What is pk of ckm? It's pk of omega to the ck of r. Now, what is this? This is by one of the lemmas. Ck of omega pk of ck of r times k plus 1. So where did I take this from? Look here. The magic lemma over here shows up. Now we have what? We have here pk of a sum. So we have to take pk of the last term in the sum. So this is omega to pk pk of r times k plus pk of the last term, omega to the pk pk of r. Now, this one here is the same as omega to ck of r minus 1 by induction hypothesis times I is k minus what is this? Here I see a problem. um, so I have to change the claim slightly. I have to see what this means. So I plug in here pk minus 1, ck of m. So is this a problem? So here's a minus 1, here's a minus 1, here's a minus 1. Here's a minus 1, here's a minus 1, here's a minus 1, here's a minus 1, so this all works. Take here now a minus 1, here now a minus 1, here now a minus 1. Then the point is here this becomes a times k. It's fine. Here's a minus 1. It's a minus 1. It's all fine. Not a problem. Okay, here's a fine. This becomes k minus 1. And what does this become? Well, what is ck of k to the r minus 1 minus 1? will be ck minus 1 of ck k to the r minus 1 by induction hypothesis, which is the same as pk minus 1 ck of so here we get omega to the ck of r minus 1. This is the same as pk minus 1 omega to pk of ck of r, pk minus 1 of ck. And so this term here is the same as this term here. So this is the same as fine. So we have shown this modified statement. Now we have to figure out what does this mean for our proof. So here this plus 2 becomes f of L plus 1. Now let's see. We have this one here. So if here is an x, we go to x minus 1. And then we jump directly to f of L. But this is just good in our case, and we have here equality. So after all these small transformations, we see finally we get what we need. We have proved finally the unprovability by a magical interweaving argument, namely here. Go from these numbers to the corresponding predecessor numbers to compare predecessor number with members of the fundamental sequence. And by good luck, we have been able to show this property. And this suffices for the proof. Okay, this is enough for this lecture. And in the next small mini lecture, I will cover the probability part. Now I'm getting tired and I will now stop for today. Okay, so I will now stop and I will continue the last part tomorrow, and I will make another